Tonight, we're going to listen to the final words of a machine that traveled farther than almost anything humanity has ever built. A spacecraft the size of a school bus, named Cassini, that spent 20 years in the dark, falling through the cold, and watching a world most of us will never see with our own eyes. And tonight, we're going to focus on the last 30 seconds of its existence, the final signal it sent back to Earth before it was torn apart by the atmosphere of Saturn. Because what Cassini did in those last moments wasn't just a graceful goodbye. It wasn't just a controlled burn-up to protect alien moons. The data it transmitted in its final breath, the readings it took while it was being ripped to pieces, contained things no one on the mission team was prepared for. Some of it was scientific gold. Some of it was unsettling. And one part of that final signal is still being argued about today, almost a decade later. Before we get started, if you find the deeper mysteries of the solar system as haunting as I do, take a second to like the video or subscribe. It's a small action, but it tells me to keep digging into stories like this one, the ones that don't make the front page. Now, let's begin. To understand why Cassini's final signal matters, you have to understand what Cassini was and where it was when it died. The spacecraft launched from Cape Canaveral in October of 1997, back when most of the people watching this video were children or hadn't been born yet. It carried instruments built by 17 different countries. It weighed about 5.5 tons at launch, much of that fuel. And it had a single purpose: to study Saturn, its rings, and its bewildering family of moons in a way no spacecraft had ever attempted. To get there, it didn't just point itself at Saturn and fly. It couldn't. It didn't have enough fuel for that. Instead, it took a strange, looping route through the inner solar system, using the gravity of Venus, Earth, and Jupiter to slingshot itself farther and farther outward. It went the wrong way first, falling inward toward the sun, before being flung back out on a trajectory that would eventually carry it nearly 1 billion miles from home. The journey took almost 7 years. When Cassini finally arrived at Saturn in July of 2004, it had already traveled about 2 billion miles, looping and turning and gathering speed. And then it stayed. For 13 more years, it orbited Saturn, dipping through gaps in the rings, skimming the cloud tops, photographing storms larger than the Earth itself. It dropped a small probe, called Huygens, onto the surface of Titan, the largest moon, where it landed on what looked like an alien beach made of frozen hydrocarbons. It discovered that Enceladus, a smaller moon, was shooting jets of water out into space from a hidden ocean buried beneath its ice. It rewrote textbooks. It changed what we thought we knew about how planets form, how moons evolve, how chemistry behaves in the cold dark of the outer solar system. But by 2017, Cassini was running out of fuel. And that was a problem. Not because the mission team wanted to bring it home. They couldn't. It had no way to return. The problem was what would happen if it kept drifting. Without fuel, Cassini would eventually become uncontrollable. It could crash into Enceladus or Titan, the two moons most likely to harbor microbial life. Earth bacteria, even after 20 years of cosmic radiation, might still be clinging to its surface. Contaminating those moons would be a catastrophe. It could compromise every future mission, every future search for alien life in those waters. So the mission team made a decision that, when you really think about it, is one of the strangest decisions in the history of exploration. They chose to kill their own spacecraft, deliberately, carefully. They plotted a trajectory that would send Cassini plunging directly into Saturn itself, where the gas giant's atmosphere would tear it apart and incinerate every microbe, every metal fragment, every trace of Earth. They called this final phase the grand finale. They timed it to extract every last second of science from a machine that knew it was about to die. On September 15, 2017, at around 7:55 in the morning Eastern Time, Cassini's signal went silent at the Deep Space Network. The room at the Jet Propulsion Laboratory in Pasadena, California went quiet. People hugged. Some cried. A 20-year project, the longest deep space mission of a generation, was over. But here is what most people don't know. The signal didn't end the way they expected it to. Cassini was supposed to stop transmitting earlier. The atmosphere was supposed to overwhelm its antenna, knock it off alignment, and silence it. Instead, Cassini fought. For about 30 seconds longer than predicted, the spacecraft kept its high-gain antenna locked on Earth and kept sending data. It was, in those final seconds, being twisted, heated, and torn apart by air thicker than anything it was designed to survive. And yet it kept talking. What it was talking about, in that last half-minute, is the question we're going to spend the rest of tonight unraveling. Because the data Cassini transmitted as it died contained measurements of Saturn's upper atmosphere that didn't match anything in the mission team's models. The chemistry was wrong. The temperatures were wrong. The way Saturn's magnetic field connected to its interior was wrong. Things that scientists thought they understood, things they had been writing about for decades, suddenly didn't fit. And there was something else. A pattern in the final readings that some researchers believe points to a phenomenon we don't yet have a name for. Something happening deep inside Saturn that, if confirmed, would change how we think about gas giants throughout the galaxy. I'm not going to spoil it yet. We'll get there. What I want you to understand right now is that Cassini's final signal was not a peaceful sign-off. It was a scream of data, compressed into 30 extra seconds, sent across 83 minutes of empty space, from a machine that was on fire and being shredded. By the time those signals arrived at the radio dishes on Earth, Cassini had already been dead for nearly an hour and a half. The signal was, in a very real sense, a message from a ghost. Photons that left a spacecraft that no longer existed, words from something already gone. And in that ghost transmission, we found things that scientists are still arguing about today. Some of them are beautiful. Some of them are deeply unsettling. And one of them, the one we're going to spend the most time on tonight, has made even the most cautious researchers wonder whether Saturn is hiding something we never expected it to hide. So tonight, we're going to walk back through it all. The mission, the discoveries, the choice to destroy the spacecraft, the final plunge, and the signal that came back. We're going to listen carefully to what Cassini said in its last 30 seconds, and we're going to find out why those 30 seconds may end up being the most important data the mission ever produced. To understand the ghost transmission, we have to go back further than the launch. We have to go back to a time when sending a spacecraft to Saturn was not a sure thing. It was barely a dream. In the early 1980s, two probes called Voyager 1 and Voyager 2 had just made their first quick passes through the Saturnian system. Their flybys lasted only hours. They sent back grainy images of the rings, blurry views of the moons, and one tantalizing photograph of Titan, an orange ball shrouded in haze so thick that the cameras couldn't see through it. Scientists were left with more questions than answers. What was under that haze? Why was Saturn's magnetic field so oddly aligned? What were the rings actually made of? How old were they? And what was happening on those mysterious icy moons? The Voyagers couldn't stay to find out. They were on a grand tour, flying past one giant planet after another, headed eventually for the edge of the solar system. To really study Saturn, someone would have to build a spacecraft that could go there and stop. Not flyby, orbit, settle in, stay for years. And that meant designing a machine more ambitious than almost anything that had been built before. The idea was floated in 1982 by a joint working group of American and European scientists. NASA would build the orbiter. The European Space Agency would build a probe to send down to the surface of Titan. The Italian Space Agency would contribute the giant high-gain antenna, the same antenna that, decades later, would broadcast Cassini's final words. They named the orbiter Cassini, after the 17th century astronomer Giovanni Cassini, who had first spotted the gap in Saturn's rings that still bears his name. The probe was named Huygens, after the Dutch astronomer Christian Huygens, who had discovered Titan in 1655. But naming a mission and building a mission are two entirely different things. Through the late 1980s and early 1990s, Cassini almost died several times before it ever flew. The project was enormous, the kind of program that costs billions of dollars and stretches across 2 decades. American politicians, looking at budget pressures, repeatedly threatened to cancel it. European partners had to lobby hard to keep their American counterparts engaged. There were arguments about scope, about cost, about whether to use nuclear power sources, about whether such an ambitious mission was even justifiable in an era when smaller, faster, cheaper missions were becoming fashionable. The nuclear question was particularly bitter. Saturn is so far from the Sun that solar panels are useless. The sunlight at Saturn is about 1% as strong as it is at Earth. A spacecraft trying to run on solar power out there would be like trying to read a book by candlelight from across a stadium. So Cassini needed radioisotope thermoelectric generators, devices that produce electricity from the decay of plutonium-238. About 73 pounds of it, sealed in ceramic pellets, shielded by layers of iridium and graphite. The activists who opposed the mission argued that if the rocket exploded on launch, that plutonium could rain down on Florida. The scientists argued that the containment systems had been designed and tested to survive any conceivable accident. The debate raged in newspapers. It made the evening news. For a moment in 1997, it seemed possible that public protest might delay or even stop the launch entirely. It didn't. On October 15, 1997, at 4:43 in the morning, a Titan IVB rocket lifted off from Cape Canaveral, carrying Cassini and Huygens into the pre-dawn sky. There were no accidents. The plutonium stayed where it was supposed to stay. The spacecraft, separated from its booster, deployed its instruments and began its long, looping journey toward the outer solar system. What most people don't appreciate is how strange that journey was. Cassini did not fly directly towards Saturn. It couldn't. The rocket that launched it didn't have enough power to send a spacecraft that massive on a direct trajectory. So Cassini had to use a technique called gravity assist, borrowing momentum from other planets by swinging close to them at carefully calculated angles. First, it flew inward toward the Sun. In April of 1998, it swung past Venus, picking up speed. Then it looped back out, and in June of 1999, it swung past Venus again. 2 months later, in August, it came back past Earth itself, so close that some people could see it in a telescope. It was briefly the fastest thing in our neighborhood, screaming past at over 40,000 miles per hour, headed outward. And then, finally, in December of the year 2000, it threaded a path past Jupiter, getting one final gravitational shove that put it on a trajectory towards Saturn. This loop took years. While it was happening, ordinary life on Earth went on. The new millennium arrived. The September 11 attacks happened. Wars started and ended. People got married, had children, grew old, died. Through all of it, Cassini was flying. Silent in the dark, occasionally pinging Earth with status updates, hibernating between events to save power. The team back at the Jet Propulsion Laboratory worked in shifts, year after year, making tiny course corrections, testing instruments, planning what they would do once the spacecraft finally arrived. And then, on July 1, 2004, after almost 7 years in transit, Cassini fired its main engine for 96 minutes straight, slowing itself enough to be captured by Saturn's gravity. This was the most dangerous moment of the mission. If the engine failed, if a fuel line ruptured, if a navigation error sent the spacecraft off course by even a fraction of a degree, everything would be lost. The team couldn't help. The signal delay between Earth and Saturn was so long, over an hour each way, that by the time anyone on Earth knew there was a problem, it would already be too late. Cassini had to do it on its own. It did. The engine fired flawlessly. The spacecraft slid into orbit, and the room at the Jet Propulsion Laboratory exploded into cheers. For the first time in human history, we had a permanent presence at Saturn, not a visitor, a resident. That arrival is where most stories about Cassini begin. It's where the famous photographs start, the swirling storms, the backlit rings, the impossible geometries of a world we had only glimpsed before. But it's important to remember what came before. The years of planning, the political fights, the plutonium debate, the 7-year flight through the dark, the hundreds of engineers and scientists who built their careers around this one machine. Some of them retired before Cassini even arrived. Some of them died. The mission outlasted its own creators, and that's what makes the final signal so heavy, in a way. By the time Cassini died in 2017, it had been built by one generation of scientists, operated by another, and was being studied by a third. Children who watched the launch on television had grown up, gone to college, gotten jobs at NASA, and were sitting in the control room when the signal finally went silent. It was a long, slow handing down of knowledge, a relay race across decades. And then, after all of that, came the data that nobody expected. The readings from the upper atmosphere, the numbers that didn't fit, the pattern in the final signal that we still cannot fully explain. Before Cassini's final plunge, scientists believed they had a fairly good picture of Saturn. Not a complete picture, not a perfect one, but a coherent one. A working model that fit into textbooks, that students learned in introductory astronomy classes, that researchers built careers around. To understand why the final signal was so disturbing, you have to understand what that picture looked like and how confident people were in it. Saturn, in the conventional view, was a gas giant, the second largest planet in the solar system, with a diameter about 9.5 times that of Earth. It was made almost entirely of hydrogen and helium, with traces of methane, ammonia, and other compounds. It had no solid surface. If you tried to land on it, you would simply sink. The atmosphere would get denser and denser as you went down, until eventually the hydrogen itself would be compressed into a strange, electrically conductive fluid known as metallic hydrogen. Somewhere deep inside, scientists believed, was a rocky or icy core, maybe 10 or 15 times the mass of Earth, buried under tens of thousands of kilometers of pressurized gas and exotic fluids. This core was the thing that had gathered all that hydrogen and helium in the first place, billions of years ago, when the solar system was young. The rings were thought to be made almost entirely of water ice, with some rocky impurities mixed in. The chunks ranged from microscopic dust to boulders the size of houses, all orbiting Saturn in a thin, flat sheet that was, in some places, only about 10 meters thick. Scientists had assumed for decades that the rings were old, formed roughly 4.5 billion years ago when the planet itself formed. They were considered a fundamental feature of Saturn, as old as the planet, as eternal as the gas giants themselves. The atmosphere, scientists believed, rotated as a coherent system. Saturn spun on its axis about once every 10.5 hours. This rotation rate had been measured by the Voyager spacecraft in 1980 and 1981 by tracking radio emissions coming from the planet's magnetic poles. Those radio bursts, called Saturn kilometric radiation, pulsed at a regular interval, and that interval was assumed to match the planet's interior rotation. The number was published. It was in every textbook. 10 hours, 39 minutes, and 22 seconds. That was how long a Saturn day was. End of discussion. The magnetic field was understood to be generated deep inside the planet, in the layer of metallic hydrogen. As Saturn rotated, the conducting fluid generated electric currents, which in turn generated the magnetic field. This is the same basic mechanism that produces Earth's magnetic field, just on a much larger scale. The field extended out into space for millions of kilometers, trapping charged particles, channeling them toward the poles, creating auroras like the ones we see on Earth, only much more powerful. The atmosphere itself was layered, scientists believed, in a fairly orderly way. At the top, where the gas thinned out into space, you had a tenuous region called the thermosphere. Below that, an ionosphere, where ultraviolet light from the sun stripped electrons off molecules. Below that, the stratosphere, then the troposphere, with its visible cloud bands and storms. The chemistry of each layer had been modeled. Researchers had written computer simulations that predicted what gases should be present at each altitude, what temperatures should prevail, what reactions should be happening. The models matched the observations well enough that nobody really questioned them. Even the moons, by 2017, were thought to be reasonably well understood. Titan had its hydrocarbon lakes and thick orange atmosphere. Enceladus had its ice and its hidden ocean and its water plumes. Mimas, with its giant crater, looked like the Death Star. Apatis had its strange two-tone surface, white on one side and black on the other. Hyperion was a chaotic, spinning sponge of porous rock. Each had been studied, photographed, mapped. There were mysteries left, of course. There always are. But the basic inventory was complete. This was the picture that scientists carried with them into the grand finale. Saturn was a known quantity. The rings were ancient. The day was 10 hours and 39 minutes. The interior was metallic hydrogen around a rock-ice core. The magnetic field came from the deep interior. The atmosphere obeyed predictable chemistry. Anything Cassini found during the final plunge, scientists assumed, would simply add detail to that existing picture. Better numbers, higher resolution. Confirmation, not revolution. There was also, frankly, a kind of confidence among planetary scientists that after 13 years of Cassini data, Saturn had given up most of its big secrets. The mission had been so productive, so revealing, that researchers expected the final phase to be more of a victory lap than a revelation. There would be discoveries, sure, but they would fit into the existing framework. The framework itself, the conceptual map of what Saturn was, seemed solid. This is a pattern in science. It happens over and over again. A field reaches a kind of plateau where the major questions seem answered, where the textbooks are written, where the consensus is comfortable. And then something happens, an observation, a measurement, a single piece of data that doesn't fit. At first, people try to explain it away. They blame instrument error. They blame model assumptions. They try to fold the anomaly back into the existing picture. But sometimes the anomaly is too big, too clear, too persistent, and the framework cracks. Going into 2017, planetary scientists were not expecting their framework for Saturn to crack. They were not expecting the textbook to need rewriting. The grand finale was designed to maximize science, to wring every possible measurement out of the spacecraft before it died. But the questions it was meant to answer were considered refinements, not revolutions. How massive was Saturn's core, exactly? How long was the day, exactly? What was the precise composition of the rings? How did the magnetic field connect to the interior in detail? These were all questions where scientists had answers, plus or minus some margin of error. The grand finale was supposed to tighten those margins. What it actually did was something different. Some of the measurements came back with values so far outside the predicted range that the researchers initially assumed something was wrong with the spacecraft. They double-checked the instruments. They reviewed the calibrations. They ran the numbers through different software. And the numbers stayed wrong, by which I mean they stayed unlike anything anyone had predicted. The rings weren't quite the age they were supposed to be. The day wasn't quite the length it was supposed to be. The magnetic field wasn't quite oriented the way it was supposed to be. The chemistry at the top of the atmosphere wasn't quite what the models said. And then, in those final 30 seconds, came the readings that pushed the strangeness past the point of comfortable explanation. The signal that the spacecraft sent as it was being torn apart contained values that, when the team finally sat down and analyzed them carefully, did not match any version of the conventional picture. Not the textbook version, not the refined version, not any version. The framework was about to crack, and it cracked in front of the entire mission team in real time as Cassini died. The cracks didn't appear all at once. They appeared slowly, one at a time, scattered across the years of the mission. And in each case, the initial reaction from scientists was the same. It must be the instrument. It must be the model. It must be something we'll figure out later. Nobody wanted to believe that the textbook was wrong. Nobody set out to overturn the consensus. The anomalies just kept piling up, quietly, in the data, until they could no longer be ignored. The first crack appeared early. Within months of Cassini's arrival at Saturn in 2004, the spacecraft's radio instruments began detecting the kilometric radiation bursts that were supposed to mark Saturn's rotation rate. These were the same pulses that Voyager had measured back in the early 1980s, the ones that had nailed down the day length at 10 hours, 39 minutes, and 22 seconds. Scientists expected Cassini to confirm that number. Instead, Cassini measured a different number. The bursts were arriving at a slightly different interval, about 6 minutes longer per Saturn day than Voyager had recorded. This was strange. Planets don't change their rotation rates. Earth's day isn't getting noticeably longer in human timescales. Jupiter rotates on a clock you could set your watch by. The idea that Saturn had slowed down by 6 minutes per day in the 23 years between Voyager and Cassini was, on its face, absurd. The mass and angular momentum required to make that happen would have torn the planet apart. So either Voyager had been wrong, or Cassini was wrong, or the most uncomfortable possibility, the kilometric radiation wasn't actually measuring the planet's interior rotation at all. It was measuring something else, something tied to the magnetic field, or the atmosphere, or some interaction between the two that drifted over time independently of the planet itself. If that was true, it meant scientists didn't actually know how fast Saturn was spinning. Not really. The number in the textbook was wrong because the method used to measure it was wrong. And without knowing the rotation rate, you couldn't calculate the shape of the planet's interior, the depth of its winds, the structure of its magnetic field. A lot of carefully constructed science suddenly had a question mark next to it. The second crack appeared in 2005 when Cassini started getting close-up looks at the rings. The conventional wisdom said the rings were ancient. They had formed alongside Saturn itself 4.5 billion years ago. That was the consensus. But Cassini's instruments could measure the mass of the rings and the rate at which they were being polluted by infalling micrometeorite dust. The math kept giving the wrong answer. If the rings were really billions of years old, they should have been much darker by now, soaked through with all the dust they had been collecting since the dawn of the solar system. They weren't. They were too bright, too clean, too pristine. The numbers suggested the rings might only be a few 100 million years old, maybe even less. Maybe they had formed when dinosaurs were already walking around on Earth. This wasn't a small adjustment. It was a complete rewrite of one of the most basic facts about Saturn. If the rings were young, then they had been made by something. A moon that had wandered too close and been torn apart. A comet that had been captured and shredded. Some catastrophic event in relatively recent geological time. And whatever process had created them was also, the data suggested, slowly destroying them. The rings were raining down into Saturn's atmosphere. Cassini measured the rate. At current rates, the rings would be gone in another 300 million years, maybe less. They were a temporary feature of Saturn. We were just lucky enough to be alive while they existed. A lot of scientists pushed back on this. Hard. The data was uncomfortable. The ring age problem implied that the standard model of how the rings formed and how long they lasted was wrong. Papers were written arguing both sides. Conferences had heated sessions where researchers presented competing analyses. Some people insisted the rings were old and the measurements were misleading. Others said the data was clear and the textbook would have to be updated. The argument is still going on today, though the evidence has tilted heavily toward the young ring's interpretation. Then came the third crack. It was about the magnetic field. Saturn's field, scientists had long known, was unusual. Most planets that have global magnetic fields have them tilted at some angle relative to the planet's rotation axis. Earth's magnetic field is tilted about 11 degrees off from the spin axis. Jupiter's is tilted about 10 degrees. The tilt is what makes a planetary dynamo work. The mismatch between rotation and magnetic axis generates the complex currents that produce a global field. Saturn's field, according to Cassini's measurements, had almost no tilt at all, as close to zero as anyone could measure. The magnetic axis was essentially identical to the rotation axis. This shouldn't have been possible. Theoretical models of planetary dynamos said that a field with no tilt couldn't sustain itself. It would decay over time. The fact that Saturn had won at all meant either the models were wrong or there was something inside the planet, some hidden layer or process that was actively keeping the tilt at zero, something nobody had predicted. By 2010, the cracks were multiplying. Cassini was sending back data on Saturn's storms that didn't match atmospheric models. The Great White Spot, a massive storm that erupts roughly every Saturnian year, appeared earlier than expected in 2010 and was more powerful than predicted. The storm released energy in patterns the models hadn't anticipated. Researchers had to scramble to update their simulations. Each time they updated, new discrepancies appeared. There were anomalies in the upper atmosphere. The temperature at high altitudes was hotter than the models said it should be. Much hotter. Sunlight alone couldn't explain it. Something else was heating the top of the atmosphere, and nobody was sure what. There were anomalies at Enceladus. The plumes coming out of the South Pole were richer in hydrogen and complex organic molecules than anyone had predicted. The hidden ocean was more chemically active than the models suggested. There were anomalies at Titan. The hydrocarbon lakes had levels that fluctuated in ways the atmospheric models couldn't fully explain. The complex chemistry in the upper atmosphere was producing molecules that shouldn't have been there. By the time the mission team began planning the grand finale in 2014 and 2015, the picture of Saturn that scientists had been comfortable with was starting to look more like a sketch, with a lot of question marks scribbled in the margins. The grand finale was meant to answer those questions, to gather data from inside the rings, from the gap between Saturn and its rings, from the upper atmosphere itself, in ways no spacecraft had ever attempted, to finally resolve the ambiguities, to either confirm the standard picture or replace it with a new one. What nobody on the team expected was that the grand finale wouldn't resolve anything. It would deepen the mysteries. It would add new anomalies on top of the old ones. And it would end with a final transmission that contained data so unexpected that, almost a decade later, researchers are still trying to figure out what Saturn was telling us as it killed Cassini. To understand how Cassini was able to discover all of this, and how it was able to send back data even while it was being destroyed, you have to look at the instruments. Not the spacecraft as a whole, but the individual machines bolted onto its frame. Each one was a tiny laboratory. Each one had been designed, built, and calibrated by teams of scientists over years, sometimes decades, and each one had a role to play in the final plunge. There were 12 scientific instruments on Cassini. The most famous, probably, was the imaging science subsystem, the cameras. Two of them, a wide angle and a narrow angle, capable of taking pictures across a range of wavelengths from ultraviolet to near-infrared. These were the cameras that produced the iconic photographs the public knows. The backlit Saturn shot, the polar hexagon, the storms on Titan, the plumes of Enceladus. But by the time the grand finale was happening, the cameras were not the primary instruments. They were useful for context, for orientation, for occasional dramatic images. The real science was being done by the other 11. There was the magnetometer, a long, thin boom that stuck out from the spacecraft, designed to measure the strength and direction of magnetic fields. To work properly, it had to be far from the rest of the spacecraft, because the spacecraft itself generated tiny magnetic fields that would have confused the readings. The boom held the sensor about 11 meters out into space, away from the noise. During the final orbits, the magnetometer was the instrument that could finally measure the magnetic field close to the planet, inside the rings, where no spacecraft had ever been. There was the iron and neutral mass spectrometer. This was the instrument that made the final transmission so important. It worked by literally sampling atoms and molecules as they hit the spacecraft, accelerating them through electric fields and measuring their charge-to-mass ratio. By doing this, it could identify exactly what gases were present in any region the spacecraft was flying through. During the grand finale, when Cassini was actually flying through Saturn's upper atmosphere, this instrument was scooping up Saturn itself and reading its composition. No previous mission had done that. Voyager had flown past. Cassini had orbited above. But the grand finale plunge was the first and only time a human-made instrument had ever directly sampled the air of Saturn. There was the cosmic dust analyzer, which could catch individual grains of dust and analyze their composition. This was the instrument that, in the years before the plunge, had measured how much micrometeorite material was raining down onto the rings. It was the instrument that had told us the rings were probably young. During the final orbits, it would tell us what the rings themselves were made of, in unprecedented detail. There was the radio and plasma wave science instrument, which listened to the natural radio emissions from Saturn's magnetosphere. This was the instrument that detected the kilometric radiation, the pulses that were supposed to mark the planet's rotation. It had been picking up signals from Saturn's environment for 13 years. During the final plunge, it would record the spacecraft's last impressions of Saturn's electromagnetic environment. And then there was the spacecraft's own radio system. The high-gain antenna, built by the Italian Space Agency, was 4 meters across, a giant dish that pointed back toward Earth. Most of the time, this antenna was used to send commands and data back and forth. But during certain critical phases of the mission, the antenna itself became a scientific instrument. By precisely measuring how the radio signal from the spacecraft was affected by passing through Saturn's atmosphere, or its rings, or even just the gravitational field of the planet, scientists could derive information about densities, temperatures, and masses. This is called radio occultation. It was one of the most powerful techniques in the entire mission. The grand finale, when it was finally designed in 2016 and early 2017, was built around all of these instruments. The mission planners drew up a series of 22 final orbits, each one carrying Cassini between Saturn and the inner edge of the rings. This gap was only about 2,000 kilometers wide. Before Cassini, nobody had ever flown through it. There were concerns that there might be unmapped ring particles in the gap, debris small enough that the cameras couldn't see it, but large enough to destroy the spacecraft on impact. As a precaution, during the first few crossings, the team rotated Cassini so that the high-gain antenna pointed forward, acting as a shield. If there were tiny dust grains in the gap, they would hit the antenna instead of the more delicate instruments. The first crossing happened on April 26, 2017. The team held its breath. The spacecraft went silent for hours as it flew through the gap. When the signal came back, the room cheered. The gap was empty, almost completely empty. The few particles that had hit the spacecraft had been microscopic. Cassini could fly through safely. From that point on, the team didn't need to use the antenna as a shield. They could point all the instruments outward, gathering data. What followed was the most productive few months of the entire mission. Each orbit took about 6 days. On each pass, Cassini got closer to the planet, dipped through the gap, and took measurements no spacecraft had ever taken. The magnetometer mapped the field at unprecedented resolution. The mass spectrometer began detecting traces of material from the rings falling inward into Saturn's atmosphere. The radio occultation experiments measured the density of the upper atmosphere with extraordinary precision. The cosmic dust analyzer caught particles flowing between the rings and the planet. By the time the final orbit began on September 11, 2017, Cassini had already gathered more data than any of its previous 12 years had produced. But the mission team wanted one more thing. They wanted to fly straight into Saturn itself, to use the spacecraft's own destruction as a final experiment, to send back direct measurements of the upper atmosphere in real time as the spacecraft burned up. This required reorienting the spacecraft for the last time. The team programmed Cassini to keep its high-gain antenna pointed at Earth, even as the atmosphere pushed it off course. The spacecraft had small thrusters, fueled by hydrazine, that could fire to keep it stable. The plan was for those thrusters to fire continuously, fighting against the atmospheric forces, holding the antenna locked on Earth so that the data could keep flowing. The team knew the thrusters would eventually lose the fight. They calculated when. They predicted the spacecraft would lose its ability to transmit at a specific moment when the atmosphere overwhelmed the thrusters. That prediction is what makes the final signal so important. The team knew when Cassini was supposed to stop talking. They had calculated the moment. They had built their models around it. The spacecraft didn't stop when it was supposed to. The thrusters fought harder than expected. The antenna held its alignment longer than the math said it should. And in those extra 30 seconds, with the spacecraft being torn apart, the instruments kept reading and the radio kept broadcasting. The Deep Space Network, with its giant antennas at Goldstone in California, Madrid in Spain, and Canberra in Australia, kept receiving. Photons that had left Cassini almost an hour and a half earlier kept arriving on Earth, carrying the final words of a machine that, by that point in real time, no longer existed. And it was in those extra 30 seconds that something showed up in the data that nobody on the team was prepared for. Section 6:15, the first major discovery from the grand finale, wasn't the kind of thing that makes headlines on the morning news. There were no dramatic photographs, no obvious wow factor. It was a chemical reading, a list of molecules, but to the scientists looking at it, it was a slow earthquake. The iron and neutral mass spectrometer had been turned on for the close passes through the gap between Saturn and the rings. As Cassini flew through that narrow strip of space, the instrument was sampling whatever was floating there. The expectation was that the gap would be mostly empty, with maybe a trace of hydrogen and helium leaking up from Saturn's atmosphere, plus some water vapor sublimating off the inner edge of the rings. That was the prediction. A clean, simple chemistry. What the instrument actually detected was a mess, a complicated, layered, unexpected mess. There was water, yes, but there was also methane. There was carbon monoxide. There was carbon dioxide. There were nitrogen compounds. And most surprising of all, there were complex organic molecules, hydrocarbon chains, the kind of carbon-rich material that scientists had not expected to find raining down from the rings. The rings were supposed to be made of water ice. Almost pure water ice, with a few impurities. They were not supposed to be dumping organic chemistry into Saturn's atmosphere by the ton. But that's what was happening. The mass spectrometer numbers translated into a stunning rate of infall. Tens of thousands of kilograms of material per second. Not per year, per second. Material from the rings was falling into Saturn at a rate so high that scientists had to recheck the calibrations before they would believe their own readings. When the calibrations checked out, the implications started to settle in. This was the phenomenon that would later be called ring rain. It had been suspected for years, ever since Voyager had detected dark bands in Saturn's upper atmosphere that some researchers thought might be the result of ring material falling in. But nobody had actually measured the rain directly. Now Cassini had done it. The rings were not just slowly fadding. They were actively pouring themselves into Saturn. The planet was eating its rings. When the first analyses came back, the team at the Jet Propulsion Laboratory got quiet. People who had been working on Cassini for 15 years sat at their desks, reading the printouts and not saying much. Hunter Waite, the principal investigator for the mass spectrometer, would later describe the moment as profoundly unsettling. The numbers were not what anyone had predicted. The composition was not what anyone had predicted. And the rate of infall meant that the rings, the iconic, beautiful, defining feature of Saturn, were on a kind of clock. They had a beginning, much more recent than anyone had been comfortable admitting, and they had an end, also closer than anyone had been comfortable admitting. But the chemistry was the part that really kept people up at night. Where were the organic molecules coming from? If the rings were just water ice, they should be releasing water vapor. Maybe some simple oxygen and hydrogen products, not hydrocarbons, not nitrogen compounds, not carbon-based chains. The most likely explanation, the scientists realized, was that the rings were not pure ice at all. They contained a significant fraction of organic material mixed in with the ice, scattered through the entire ring system. This material had probably come from the original body that had been destroyed to make the rings in the first place. A moon, a captured comet. Something with a rich, complicated chemistry, torn apart by tidal forces and spread out into a glittering disk. The organic compounds had been there for millions of years, locked into the ice, slowly bleeding off into space as the ring particles ground against each other and ablated under sunlight. This had profound implications. Because if the ring particles contained organic compounds, and if those compounds were now raining down into Saturn's upper atmosphere, then Saturn's atmosphere was being seeded in real time with the chemistry of life. Not life itself, not even the building blocks of life in any complete sense, but the same kinds of carbon-rich molecules that, on Earth and on Titan, were known to assemble themselves into more complex compounds under the right conditions. Researchers began talking, carefully and tentatively, about the possibility that the upper atmosphere of Saturn might host some kind of unusual photochemistry. Not biology, nobody was suggesting that, but a richer chemical environment than anyone had imagined. Where ring rain met sunlight at the top of the atmosphere, complex reactions could be happening continuously, new molecules forming, old ones breaking apart. A chemistry shop running on the boundary between the planet and its dying jewelry. That alone would have been enough to rewrite chapters of the textbook, but the mass spectrometer kept finding more. There were heavier molecules in the readings, molecules that the team initially couldn't even identify. The mass numbers were in a range that the instrument had been designed to detect, but the patterns didn't match anything in the standard chemistry references. Methane, the team understood. Ammonia, the team understood. But there were peaks at higher masses, in patterns that suggested clusters of carbon, hydrogen, oxygen, and nitrogen, bound together in configurations that didn't appear in any of the predicted models. Some of these clusters had the molecular signatures of compounds that, on Earth, are associated with biological processes. To be absolutely clear, nobody on the Cassini team was claiming that the rings contained life or that anything biological was happening on Saturn. The molecules in question can also form non-biologically through purely chemical pathways, given the right conditions. But finding them in the gap between Saturn and its rings, falling toward the planet, was not what anyone had expected. It was the kind of finding that, when researchers presented it at scientific conferences, made other scientists lean forward in their chairs. The immediate reaction from the broader scientific community was a mixture of excitement and skepticism. Some researchers wanted to wait. They argued that the mass spectrometer might be picking up contamination, that the readings could be the result of outgassing from the spacecraft itself as it heated up during the close passes. The instrument team pushed back. They had calibrated the instrument carefully. They had compared the close pass readings with readings taken farther out. The chemistry inside the gap was clearly different from the chemistry outside it. The signal wasn't contamination. The signal was real. Within months, the first peer-reviewed papers were being submitted. Within a year of the mission ending, the basic finding was established. The rings were eating themselves and falling into Saturn at a furious rate. The infalling material contained a complex chemistry. The upper atmosphere of Saturn was being chemically transformed in ways that previous models had completely missed. The textbook needed a new chapter, and this was only the first revelation. The first piece of the grand finale data set. There were still hundreds of gigabytes of measurements to work through. The magnetometer was still being analyzed. The radio occultation data was still being modeled. The final 30 seconds of transmission, the ones that came after the spacecraft was supposed to have gone silent, hadn't even been fully processed yet. The team did not yet know that what they had found in the ring rain was, in retrospect, the easy discovery. The next one would be harder to accept, and the one after that would be harder still. The second discovery came from a completely different instrument, and it cut deeper in every sense. It came from the radio system, from the way Cassini's voice changed as it spoke to Earth. Throughout the grand finale, mission scientists had been doing what is called gravity science. The technique is elegant and strange. As Cassini orbited Saturn, the spacecraft's path was being shaped by Saturn's gravitational field. If Saturn's mass were perfectly uniform, evenly distributed inside the planet, the field would be a smooth, simple thing, and Cassini's orbit would be predictable down to the millimeter. But mass inside a planet is never perfectly distributed. There are denser regions and lighter regions. There are flows and currents and layered structures. Each of these tugs on the spacecraft a little differently as it passes by. By measuring the tiny variations in Cassini's velocity, scientists could map the inside of Saturn the same way a doctor might use ultrasound to map the inside of a body. The radio signal itself was the measurement tool. As Cassini sped up or slowed down by even a fraction of a millimeter per second, the frequency of its radio transmissions shifted by a corresponding fraction. The team on Earth could measure those shifts with extraordinary precision. For 13 years, the gravity science team had been gathering data from Cassini's more distant orbits. They had built a rough map of Saturn's interior, but the grand finale was the moment they had been waiting for. During the close passes, the spacecraft was skimming so near to the planet that the gravity measurements would be sharper than anything ever obtained for any gas giant. The team would finally be able to see, with real resolution, what Saturn was made of inside. What they expected to find was a fairly standard gas giant structure, an outer envelope of hydrogen and helium growing denser with depth, a layer of metallic hydrogen, the conducting fluid that was supposed to be generating the magnetic field, and at the very center, a compact rocky or icy core, 10 or 15 Earth masses worth of solid material, the original seed around which the gas had collected billions of years ago. This was the textbook model. It was also the model that scientists had been confident in for decades, the model that informed every theory of how giant planets form throughout the universe. The gravity measurements came back, and the textbook model didn't fit. The first thing that emerged from the data was the depth of Saturn's atmospheric winds. The visible bands you see in pictures of the planet, the cream and gold and tan stripes, are driven by powerful jet streams in the upper atmosphere. Scientists had long debated how deep those jets penetrated. Were they only a thin skin, a weather pattern in the cloud tops, Or did they extend much deeper, going thousands of kilometers down into the planet? The answer mattered because it determined how much of Saturn's mass was actually rotating with the visible atmosphere, and how much was a deeper, more uniform interior beneath. The gravity data gave a clear answer. The winds went down about 9,000 kilometers. That is roughly 1.5 times the radius of Earth, all of it actively flowing, all of it part of the dynamic, banded atmosphere. The gas giant wasn't a thin layer of weather over a quiet body. The weather was a third of the way to the center. The atmosphere was the planet, for an enormous depth, with jets and circulation patterns reaching down into pressures and temperatures that would crush any human-made instrument instantly. This was startling enough on its own. But the deeper measurements gave something even stranger. When the team pushed the gravity model further, trying to characterize what was below the wind layer, they found that there was no clean transition to a rocky core. There was no sudden boundary, no surface where the gas met the rock. Instead, the densities increased gradually, smoothly, through layer after layer, with rock and ice and gas all blending together in proportions that changed continuously with depth. The center of Saturn was not a discrete core surrounded by a gas envelope. The center of Saturn was a vast, smeared-out region where rocky and icy material was diluted into the hydrogen and helium, gradually concentrating but never quite forming a hard boundary. Scientists started calling it a fuzzy core. The term stuck. It is now the accepted description of what is at the center of Saturn, and probably at the center of Jupiter as well, and probably at the center of countless gas giants throughout the galaxy. The textbook picture of a clean rocky kernel surrounded by hydrogen had been wrong. Instead, there was a slowly graded mixture, a smear that filled half the planet, with rocky elements distributed throughout the hydrogen in a way no model had predicted. The implications for planet formation were significant. The standard theory of how gas giants form had assumed that a rocky core formed first, gathered enough mass to capture huge amounts of hydrogen and helium from the surrounding nebula, and then settled into a stable layered structure. The fuzzy core finding suggested that either this process happened very differently than scientists had thought, or that something had happened later in the planet's history, perhaps a giant impact early in the solar system that had broken up an existing core and mixed it into the surrounding gas. Either way, the simple model didn't work. Saturn's interior had a more complicated history, and there was more. By combining the gravity data with the magnetometer readings, the team could finally pin down something that had been frustrating scientists for decades: the true rotation rate of the planet. Not the rate of the kilometric radiation bursts which had drifted over time, but the actual rate at which the deep interior was rotating. The number came out to 10 hours, 33 minutes, and 38 seconds. About 6 minutes shorter than the value that had been in textbooks since the 1980s. 6 minutes does not sound like much, but it changed the calculated shape of the planet, the structure of its winds, the depth of its atmospheric layers, the energy balance between the equator and the poles. Every previous model that had used the old rotation rate had been built on a slightly wrong foundation. None of the conclusions were catastrophically incorrect, but all of them had to be revised. Papers from the past 20 years had to have their numbers updated. Theoretical frameworks had to be recalibrated. Within the planetary science community, the discoveries from the gravity data were not universally celebrated at first. Some researchers had built careers around the older models. The fuzzy core idea was, for some, a difficult thing to accept. It implied that gas giants were not as well understood as had been claimed. It implied that the standard theory of planet formation had a serious problem at its center, literally and figuratively. There were conferences where the new results were debated with intensity. There were rebuttals and counter-rebuttals. But the data, as the months went on, kept holding up. Independent analyses gave the same answers. The fuzzy core was real. By 2019, 2 years after the spacecraft died, the new picture of Saturn was taking shape. The planet had ancient, smeared-out interior, deep winds reaching thousands of kilometers down, and a rotation rate that had been wrong in every textbook for a generation. 3 major facts about Saturn, all revised, and the team still had not finished analyzing the final 30 seconds. The third discovery is where the pattern began to emerge. Not just one anomaly, not just two, but a coherent shape forming across all the data sets. Saturn was telling the team something. They could hear the message starting to take form. They were not yet sure what it meant. This time the data came from the magnetometer, the instrument on the end of the long boom. During the grand finale, the magnetometer was finally able to measure Saturn's magnetic field from inside the rings, at distances no spacecraft had ever achieved. The measurements that came back confirmed, with brutal precision, something that had been suspected for years but never definitively established. Saturn's magnetic field was almost perfectly aligned with its rotation axis. The tilt between the two axes was less than 0.0095 degrees. To put that in human terms, if you held up a needle representing the magnetic axis and another needle representing the rotation axis, the angle between them would be less than the angle subtended by a grain of sand viewed from across a football field. The two axes were, for all practical purposes, the same line. This should not be possible. There is a theorem in physics called Cowling's theorem, named after the British astrophysicist Thomas Cowling, who proved it in 1933. The theorem states that a purely axisymmetric magnetic field, a field perfectly aligned with the rotation axis of the body that generates it, cannot be sustained by a self-exciting dynamo. The math is clean and ruthless. If a planet's magnetic field is perfectly aligned with its spin, then the internal flows that normally generate the field have no asymmetry to work with. The field cannot regenerate itself. It will decay. Over geological time, it will fade to nothing. Saturn's field had been around for billions of years. It was strong, stable, and clearly being actively generated. And yet it was aligned to within 1/100th of a degree of the rotation axis. By Cowling's theorem, this was, strictly speaking, impossible. When the final measurements came back from the magnetometer team, there was a quiet panic among the dynamo theorists. The implications were enormous. Either Cowling's theorem was wrong, which seemed unlikely after almost a century of confirmation, or there was something inside Saturn that the standard models had missed entirely. Some hidden mechanism. Some layer or process that was generating the field in a way that didn't follow the standard dynamo rules. Theories began to multiply. One idea was that Saturn might have a stable layer somewhere in its interior, a region where helium was settling out of the hydrogen and falling toward the center, creating a horizontal flow pattern that smoothed out any asymmetry in the deeper field before it reached the surface. This would explain why the field looked symmetric from outside, even if the underlying dynamo was tilted. The deep field would be hidden, masked by an electrically conducting layer that erased the tilt. It was a clever explanation, but it required a layer that had never been directly observed, and that had to have very specific properties to do the job. Another idea was that the field really was being generated in an unusual way, by mechanisms that involved both the deep interior and the upper atmosphere working together. Some researchers proposed that the powerful winds at the cloud tops, which Cassini had now shown extended down 9,000 kilometers, were themselves part of the dynamo system. Charged particles in those winds, dragged along with the atmospheric flow, could be contributing to the generation of the field in ways that no previous model had included. A third possibility was even stranger. Some theorists suggested that the apparent alignment was a snapshot of an oscillation. Saturn's field, in this view, might be slowly tilting and untilting over thousands or millions of years, passing through phases of near-perfect alignment between phases of greater tilt. Cassini might simply have been lucky enough to arrive during one of the quiet phases. If this were true, the field should be tilted again at some point in the geologically near future, and the alignment should shift over time in a way that could eventually be detected. None of these ideas had clean experimental support. They were all attempts to explain a fact that, by the rules of classical dynamo theory, should not exist. Saturn's magnetic field was a problem. A problem that, after Cassini's death, was now sharper and more undeniable than ever. Here is where the pattern began to coalesce. The team started to see a thread connecting the magnetic field anomaly to the other grand finale discoveries. Saturn, it turned out, was a planet of blurred boundaries. The interior had no clean core, just a fuzzy gradient that blended rock and ice into the gas. The atmosphere had no clean bottom, with winds extending thousands of kilometers down into the interior. The rings had no clean separation from the atmosphere, with ring material continuously raining down and atmospheric chemistry being transformed by it. And now, the magnetic field had no clean tilt, with rotation and magnetism perfectly coupled in a way that the standard physics said could not be self-sustaining. The pattern was this. Saturn does not have the discrete, layered, well-defined structure that the textbooks had drawn for decades. Saturn is a system of interconnections, of smooth gradients, of couplings between regions that should, by classical theory, be separate. The rings are connected to the atmosphere. The atmosphere is connected to the deep interior. The interior is connected to the magnetic field. And the whole thing operates as a single, integrated system in which no boundary is as sharp as the diagrams had made them look. This was, in some ways, a beautiful realization. It suggested that the giant planets were richer and more dynamic than anyone had given them credit for. It suggested that planet formation, planet evolution, and planet physics all involve processes that link interior to atmosphere to surroundings in continuous feedback loops. It suggested that the universe of planets was more elegant, more woven than the simple textbook pictures. But it was also unsettling, because if Saturn was operating as an integrated system in ways nobody had fully understood, then there might be other things happening deeper in the system that nobody had detected at all. The discoveries of the grand finale were significant, but each of them raised the question of what else might be hiding in the data. What else might be coupling regions of the planet together in ways the team had missed? And it was at this point in the analysis, with the pattern of interconnection emerging across the data sets, that the team began to take a serious look at the final transmission, the last burst of measurements, the 30 seconds that nobody had expected to receive. Up until then, those final readings had been treated as a footnote, a poignant detail of the mission's ending. The mass spectrometer had been recording right up to the end. The magnetometer had been recording. The radio system itself had been recording. There were values in the data, numbers that had come in during the final fight against the atmosphere. Now those numbers were getting a second look, and the team was about to discover that the final 30 seconds contained the strangest reading of the entire mission, a signal that did not fit any of the patterns. A measurement so unexpected that even the researchers who first saw it asked, for several days, whether it could possibly be real. The fourth discovery did not announce itself. It hid in the data for months before anyone realized what they were looking at. The team had been busy with the earlier findings, the ring rain, the fuzzy core, the magnetic field puzzle. The final 30 seconds of transmission had been archived, processed in routine ways, and set aside for later detailed analysis. By the spring of 2018, several teams had begun to dig into those last readings carefully, going through them one variable at a time, comparing them to the predictions, looking for anything that needed explanation. The first thing that caught attention was a temperature reading. As Cassini plunged into the upper atmosphere, the sensors had been recording the temperature of the surrounding gas. The team had a model. They knew more or less what the temperatures should look like as the spacecraft descended through different layers. The upper atmosphere of Saturn should have been cold by gas giant standards, a few hundred degrees above absolute zero, with a clear gradient as you went deeper into denser air. The numbers should have followed a smooth curve, predictable from physics. The numbers did not follow a smooth curve. At certain altitudes, the temperatures spiked, not enormously, not in ways that would have been obvious at first glance, but the spikes were there, consistent across multiple sensors, and they occurred at altitudes where, according to the models, nothing should be heating the atmosphere. The sun was not strong enough at Saturn's distance to produce this kind of heating. The atmosphere should have been radiating away whatever heat it absorbed, settling into the calm thermal profile that the models predicted. Instead, certain layers were running hotter than they had any right to be. This was not a new mystery, exactly. For more than 30 years, scientists had known that the upper atmospheres of the gas giants were hotter than solar heating alone could explain. The problem had a name. It was called the energy crisis of the giant planets. Saturn, Jupiter, Uranus, Neptune. All four of them had upper atmospheres that were hundreds of degrees warmer than the Sun should be able to produce at their distances. Something else was heating them. For decades, theorists had argued about what that something else might be. Some thought it was the auroras, the same particle-driven light shows that produce the northern lights on Earth, dumping energy into the upper atmosphere at the poles. Some thought it was wave energy propagating up from the lower atmosphere. Some thought it was electromagnetic coupling with the magnetic field. Nobody had a definitive answer. Cassini's final readings, properly analyzed, gave the strongest evidence yet that the heating was real, was happening at specific altitudes, and was occurring even at non-polar latitudes where the auroras could not be the explanation. Saturn was warming its own upper atmosphere through some mechanism that, in 2018 and still today, nobody can fully account for. The final descent had captured the heating in action, in detail, at the moment of the spacecraft's death. But the temperature spikes were not the strangest part of the final transmission. The strangest part was the chemistry that arrived alongside them. The mass spectrometer, even as it was being battered by the atmosphere, had continued to read out the molecular composition of the surrounding gas. In the last 30 seconds, as Cassini fell into denser and denser layers, the readings showed an explosion of molecular signatures. Hundreds of peaks at different mass numbers. Some of them corresponded to expected molecules: hydrogen, helium, methane, ammonia. But many of them did not. There were peaks at mass numbers that did not match any of the predicted compounds for that depth and that temperature. There were patterns of peaks that suggested heavy organic molecules, complex chains of carbon and hydrogen, in concentrations that nobody had expected to find in the upper atmosphere of a gas giant. The chemistry models for Saturn's upper atmosphere predicted a relatively simple environment. Photochemistry driven by sunlight should produce certain known compounds. Diffusion from below should bring up certain known gases. The combination should give a specific, predictable mix. The final transmission showed a chemistry that was richer, more layered, and more diverse than the models allowed. The peaks at higher mass numbers were particularly puzzling. They suggested molecules with structures that should not have been stable at the temperatures and pressures the spacecraft was passing through. One particular pattern in the data drew the most attention. There was a cluster of peaks that, when researchers tried to match them to known compounds, kept producing matches with molecules associated, on Earth and on Titan, with photochemical processes that produce the building blocks of complex organic chemistry. Compounds related to aerosol formation. Compounds that, on Titan, are part of the chain that builds up the famous orange haze, the slowly assembling soup of organics that some researchers think could mimic the chemistry of early Earth. The team was careful here, extremely careful. The mass spectrometer measures mass-to-charge ratios. Two completely different molecules can have the same mass and produce the same peak. The instrument cannot tell you, with absolute certainty, which molecule is responsible for a given signal. Multiple interpretations are possible, and again, no biology was implied. Nobody was suggesting that Saturn's upper atmosphere harbored life, but the patterns suggested a chemistry far more elaborate than expected. And then there was the thing that, more than anything else, kept the team coming back to the final 30 seconds. There was a coupling between the temperature spikes and the molecular peaks. The places where the atmosphere was unexpectedly warm were also the places where the unexpected molecules were most concentrated. The two anomalies were correlated. Wherever Cassini detected an elevated temperature, it also detected elevated complexity in the chemistry. The two were happening together, in the same layers, in the same regions of the descent. This suggested that whatever was heating the upper atmosphere was also, somehow, driving the unusual chemistry. The two were linked. Some process, currently unidentified, was depositing energy into specific regions of the atmosphere and also producing or sustaining a molecular environment that the standard models had not predicted. The energy crisis and the unexpected chemistry were not two separate problems. They were two faces of the same problem, and the final transmission, the 30 seconds of ghost data, was the place where the two faces lined up most clearly. When the team finally wrote this up, in a series of papers that began appearing in 2019 and 2020, the language was cautious. The papers used phrases like unexplained heating signature and anomalous molecular abundances and unidentified atmospheric processes. The authors were careful to list every possible mundane explanation. Instrument artifacts, contamination from the spacecraft itself as it heated up, calibration drift, statistical noise. They examined each of these possibilities, and in each case, found that the anomalies were too consistent, too coherent, too well correlated to be artifacts. Something real was happening in Saturn's upper atmosphere, something that produced both heat and complex chemistry in linked patterns, something the team could measure but could not yet explain. By the time these papers were being published, the broader implication was starting to settle in. The pattern of interconnection that had emerged from the earlier discoveries had now extended into territory that physics had not mapped. Saturn was operating as a coupled system, yes, but the couplings were producing effects that current models could not reproduce. The energy budget did not balance. The chemistry did not match. The final 30 seconds were not just a poignant goodbye. They were evidence of a working planet doing something no theorist had predicted. And the team was about to face one more reading, one last anomaly from the final descent, the one that would prove the hardest to explain of all. The final reading was not, by itself, the most spectacular piece of data Cassini sent back. It was a number, a measurement of the rate at which ring material was crossing into the upper atmosphere, derived from the very last seconds of the mass spectrometer's output. When combined with the gravity measurements of the ring system, which had also come from the grand finale, it produced a result that, when the team finally calculated it, made them stop and look at each other across the room. The total mass of Saturn's rings, as determined by Cassini's gravity science, was small, much smaller than anyone had assumed. About 40% of the mass of my mass, which is itself one of Saturn's smaller moons, only about 400 kilometers across. The entire glittering ring system, the most famous feature of any planet in the solar system, the thing that decorates every poster and every astronomy book, contained less material than half of a single mid-sized moon. The rings were beautiful, but they were not massive. When the team divided the ring mass by the rate at which the rings were losing material through ring rain, they got a number that nobody wanted to believe. The rings would not last billions of years. They would not last hundreds of millions of years. They would last, at the current rate of loss, somewhere between 100 million and 300 million years from now. After that, they would be gone. Saturn would be a bare gas giant, no rings, no glittering disk, like Jupiter, like Uranus, like every other gas giant that humans have ever seen up close. And going backward, the same math produced an even more unsettling number. The rings could not have been around forever. They could not have formed alongside Saturn 4.5 billion years ago, because they would have rained themselves into the planet long before now. Working the numbers backward, the rings had to be young. The best estimates put their age at somewhere between 100 million and 400 million years. The most likely value was around 150 million years. 150 million years ago. This is the number that reframes everything. 150 million years ago, the dinosaurs were not the ancient ancestors of legend. They were alive. They were walking across continents that themselves were arranged in shapes that no living human has ever seen on a globe. Pangaea was breaking apart. The Atlantic Ocean was just beginning to open. The first birds were evolving from small theropod dinosaurs. The world was warm, swampy, populated by giants. And during all of that, Saturn had no rings. The planet you see in every photograph, the most iconic image in astronomy, did not look like that yet. Then, sometime in the middle of the dinosaur era, something happened at Saturn. A moon, possibly, or a captured comet, or a chunk of icy debris from somewhere in the outer solar system. Whatever it was, it strayed too close to the planet, and Saturn's gravity tore it apart. The fragments spread out into a disk. They began to grind against each other, breaking down into smaller and smaller pieces, eventually settling into the thin, bright, organized ring system we see today. Saturn became Saturn, the planet with rings, only after this event. For most of its history, it had been a featureless gas giant, like the others. And now, in our time, in the few brief millennia of human civilization, those rings are dying. The same processes that built them are tearing them apart. The infall rate Cassini measured is so high that the rings are essentially a temporary feature. They will not survive to see whatever life evolves on Earth a few 100 million years from now. If our descendants, or some other intelligent species, look at Saturn through their telescopes in 200 million years, they will see a bare planet. They will not know it ever had rings unless they look very carefully at thin chemical traces in the upper atmosphere, the fossil residue of a glittering disk that vanished before they were born. This was the moment, in the analysis of the grand finale data, when the team understood what they had really seen. They had not just measured a planet. They had not just refined the textbook. They had caught Saturn in the middle of an event, a transient. A brief, beautiful, dying spectacle that humans had been lucky enough to look up and see. Every photograph ever taken of Saturn with its rings, going back to Galileo's first confused observations through his telescope in 1610, has captured a planet in the middle of a process. Galileo could not figure out what he was seeing. His telescope was too crude. He thought Saturn had ears or handles or two smaller companions on either side. When the rings tilted edge-on a few years later, they disappeared, and he doubted his earlier observations. He died never quite understanding what he had seen. But Galileo, like every astronomer after him, was looking at something that had existed for less than the duration of the dinosaur era. He was looking at something that, on the timescales of the solar system, was almost brand new. And he was looking at something that was already, even as he turned his telescope, slowly bleeding itself into the planet. The grand finale data made this concrete. We were not observing Saturn in a steady state. We were observing Saturn during the brief, glittering middle of an event whose beginning and end were both invisible to us. The rings, the chemistry, the ring rain, the heating in the upper atmosphere, the coupling between regions of the planet, the strange molecular signatures in the final 30 seconds, all of it might be different in another 200 million years. We are not looking at the typical Saturn. We are looking at the Saturn of right now, a configuration that has existed for a short time and will end in a short time. When the implications of this began to spread through the planetary science community, the response was a mixture of awe and discomfort. The awe was obvious. There is something profound about realizing that the most famous feature of the most famous planet in our solar system is a temporary spectacle, a cosmic event that humans happen to be alive for. The discomfort was subtler, because if Saturn's rings are temporary, then maybe other features of other planets are temporary too. Maybe what we see when we look at any world is just a slice of a longer process we cannot detect. Maybe the universe of planets is more dynamic, more transient, more event-driven than the textbooks have ever drawn. And then there was the question that the discovery raised most sharply. If the rings are young, then the event that created them happened in geologically recent time. It happened during a period when life on Earth was already complex. It happened in the same era as the dinosaurs. Something destroyed a moon, or captured a body, or shattered a piece of ice, while creatures with backbones and brains were walking around on Earth. Whatever caused the rings to form is not an ancient mystery from the origin of the solar system. It is a relatively recent event. It happened in our local cosmic neighborhood in a time period we can actually imagine. That event left no other clear trace. It produced the rings, and then it ended, and the rings have been bleeding into Saturn ever since. Cassini watched the bleeding. Cassini measured the bleeding. And in its final 30 seconds, Cassini fell into the place where the bleeding was happening and sent back the last numbers from the inside. Section 1115, the cumulative effect of these discoveries did not arrive all at once. It built up over years, paper by paper, conference by conference, as the planetary science community absorbed what Cassini had revealed. By the early 2020s, several frameworks that had been considered settled were no longer settled. Entire chapters of textbooks had been quietly rewritten. New courses were being designed around concepts that did not exist when the mission ended. The first framework to break was the standard model of how giant planets form. For decades, the going theory was called core accretion. The idea was clean. In the early solar system, dust grains around the young sun stuck together to form pebbles. Pebbles stuck together to form rocks. Rocks gathered into larger and larger bodies until, in the outer disk, a few of them grew massive enough, perhaps 10 Earth masses, to begin pulling in hydrogen and helium from the surrounding nebula. Those bodies grew into the gas giants. At the heart of each, the old rocky seed remained, surrounded by a thick envelope of gas. Clean, simple, logical. Cassini's fuzzy core finding did not destroy this picture, but it severely complicated it. If Saturn's interior is a smeared gradient rather than a clean, layered structure, then either core accretion does not produce the layered planets it was supposed to produce, or something happens after formation that mixes the layers together. Some researchers now think that giant impacts in the early solar system, collisions between protoplanets, may have shattered original cores and stirred their material into the surrounding gas. Others think the mixing happens continuously through convection over billions of years. Still others wonder whether the original models simply had the formation sequence wrong, and gas and rock were accreting more simultaneously than was previously believed. The argument is unresolved. But the days when researchers could draw confident cross-section diagrams of gas giant interiors are over. The second framework that fractured was the long-standing assumption about planetary rings. Rings, by the old view, were ancient. They were leftovers from the formation of the solar system, primordial debris that had never quite organized into moons. This assumption shaped how researchers thought about ring dynamics, ring chemistry, and ring evolution. It also shaped how they thought about other ring systems in the solar system and beyond. Jupiter has rings, Uranus has rings, Neptune has rings. Researchers tended to treat all of them as old. Cassini's data has now flipped that assumption. If Saturn's rings are young, then the rings of the other giant planets might be young too. The faint, dark rings of Jupiter, Uranus, and Neptune may have formed in recent geological time, the product of relatively modern events. Each gas giant in the solar system may have its own ring history, marked by individual collisions and tidal disruptions in the last few 100 million years rather than ancient remnants from the planet's birth. Astronomers are now looking at ring systems with fresh eyes, asking when, not just how. Some studies are now exploring the possibility that ring systems may come and go on geological timescales, that the absence of rings around a planet today does not mean the planet never had them. Earth itself might have had rings briefly after the impact that formed the moon. Mars might have rings in the future when its moon Phobos eventually breaks apart. The solar system, in this view, is not a static collection of features. It is a slow, ongoing performance. The third framework that took damage was classical dynamo theory. Cowling's theorem stands. The math is right. But Saturn's perfectly aligned magnetic field, generated by a planet that has obviously had this field for billions of years, requires some addition to the theory that nobody yet has nailed down. The most popular current explanation involves a stable conducting layer between the dynamo region and the surface, smoothing the apparent tilt and hiding the deeper asymmetry. If this idea holds up, it implies that other planets, including Jupiter, Earth, and the magnetized exoplanets we are starting to detect, may have similar hidden layers that we have never directly observed. The geometry of every planetary magnetic field becomes a different kind of question. Researchers are not looking at the field that the dynamo produces. They are looking at the field that survives passage through whatever lies above the dynamo. And that distinction, before Cassini, was barely acknowledged. The fourth framework, the one that may have changed the most in ways the public does not see, is the conceptual model of what a planet even is. The old picture treated planets as objects, solid bodies, or fluid bodies, or layered bodies, with surfaces and interiors and atmospheres that could be described separately. Cassini has helped push the field toward thinking of planets as systems, open systems. Systems that exchange material and energy with their surroundings, that couple their atmospheres to their interiors, to their magnetic fields, to whatever rings or moons happen to be nearby. Saturn is not a planet plus rings plus moons. Saturn is a single thing. The rings are part of the planet. The moons feed material into the rings. The rings feed material into the atmosphere. The atmosphere feeds material into the magnetic field. The magnetic field guides material between the moons. The whole system loops back into itself. This new way of thinking has practical consequences. When researchers model exoplanets, planets around other stars, they now have to think about what features might be transient. They have to ask whether the data they collect represents a snapshot of a long-running configuration or a glimpse of a passing event. They have to consider whether the strange features they see in some exoplanet observations, the unexpected light curves, the puzzling spectral signatures, might be the result of temporary phenomena, like ring systems forming and dissipating, like atmospheres being chemically transformed by recent impacts. Cassini taught the field that planets can be surprising on timescales much shorter than billions of years. There are also implications for the search for life. Saturn itself is not a place where biology is plausible. The temperatures and pressures inside the planet are extreme. The upper atmosphere, despite its unexpected chemistry, is not a stable enough environment for organisms to develop. But the discovery that the upper atmosphere is being continuously transformed by ring infall, that complex organic chemistry is happening at altitudes where the standard models predicted simple gases, has implications for how researchers think about chemical evolution in general. If a gas giant can host an unexpectedly elaborate chemistry in its upper atmosphere, then chemical complexity may be more widespread in the universe than the old models suggested. The conditions that produce organic molecules may not require terrestrial planets or warm oceans. They may arise wherever the right materials are mixing under the right energy gradients. And then there is what Cassini did to the moons. The discovery that Enceladus is an active world with a subsurface ocean and hydrothermal activity has made Enceladus one of the leading candidates for finding life beyond Earth. Titan, with its hydrocarbon lakes and prebiotic chemistry, is now the target of an upcoming mission called Dragonfly, which will fly a drone-like vehicle across its surface in the 2030s. Cassini did not directly find life, but it changed the list of places where life might be found. Before Cassini, most discussions of astrobiology focused on Mars and Europa. After Cassini, Enceladus and Titan are at the top of the list. In aggregate, the discoveries from the mission, capped by the strangeness of the final transmission, have reshaped planetary science from the inside. Most of the changes have not yet trickled into popular awareness. The textbooks are slow to update, but within the field, the consensus that existed before Cassini is gone. A new, more dynamic, more uncertain consensus is taking shape. And much of it traces back to those final seconds of data, the ones that made the team look at Saturn and see, for the first time, a planet that was still hiding. It is worth pausing here and asking why any of this should matter to a person who is not a planetary scientist. Why should it matter to you, sitting somewhere on Earth, in the middle of an ordinary day or an ordinary night, that a spacecraft died at Saturn almost a decade ago and sent back numbers that rewrote some textbooks? Saturn is far away. You will never visit it. The rings will exist or not exist long after you are gone. Why is any of this personal? I would argue it is personal in a way that almost nothing else in modern science is personal. Because what Cassini taught us, more than any of the specific scientific revisions, is something about the nature of being alive. For most of human history, the night sky was understood as eternal. The stars in their patterns, the planets in their orbits. Saturn with its rings, once humans had telescopes good enough to see them, became part of the permanent furniture of the cosmos. Generations of poets, astronomers, philosophers, and ordinary people looked up and felt the comfort of knowing that the sky was older than they were, and that it would still be there long after they were gone. That permanence was a kind of consolation. The universe was vast and unchanging, and our brief lives were small but situated within something stable. Cassini broke that picture in a specific, quiet way. It did not break it by revealing a violent or chaotic cosmos. It broke it by revealing a slowly changing one. The most iconic feature of our solar system, the rings of Saturn, are not eternal. They are not even old. They appeared in geologically recent time when our planet was already populated with complex life. They are dying. They will be gone in a span of time that, while long compared to a human lifetime, is short compared to the age of the universe. Humans, for the entire span of our existence as a species, have been alive during a Saturn that has rings. We are observing a passing show, and the show began not long before us and will end not long after us. This changes the texture of what it means to look up. When you see Saturn through a small telescope, when those rings resolve themselves into the sharp, impossible shape that has been on every astronomy poster for 200 years, you are seeing something that, in cosmic terms, is brand new. You are seeing something temporary. You are looking at a brief, glittering accident in the long life of a planet that had been bare and would have stayed bare except for a chance encounter sometime during the Jurassic. You are looking at a thing that, by all the standards of cosmic time, just got here, and it is leaving. There is something humbling and beautiful in this. It is the realization that the universe is not just enormous and old. It is also full of brief, gorgeous events, things that arise and pass, things that are happening on schedules nobody set, that we can witness for a moment, and that will be replaced by other things long after we are gone. The Earth itself is full of these brief beauties: coral reefs, migrating swarms, glaciers, forests, our own civilizations. None of them are eternal. All of them are temporary. The instinct to think of the natural world as permanent is, like the instinct to think of Saturn's rings as ancient, a kind of optical illusion produced by the shortness of our own lives. The rings of Saturn make this concrete in a way that almost nothing else can. They are so far away, so removed from our daily concerns, that we have no investment in their permanence. We did not build them. They do not produce our food or filter our air. They are not part of any human story. And yet, knowing that they are temporary, knowing that the planet on our textbook covers had no rings during the dinosaur era and will have no rings during the next geological epoch, gives us a kind of cosmic mirror. It reminds us that even the most famous, most reliable, most photographed objects in the universe have schedules. They have beginnings and endings. They are passing through. There is also a more direct lesson. Cassini was built and operated by humans. The discoveries it made are now part of our shared knowledge as a species. Every person reading or watching this is now in possession of information that no human had before 2017. Every one of us, on some level, knows things about Saturn that Galileo, Newton, Kepler, and Einstein never knew. The rings are young. The interior is fuzzy. The atmosphere is being chemically transformed by something falling from above. These are facts that we have, that none of our great predecessors had, because we sent a robot to find out, and the robot found out, and then the robot died doing it. This is what science does at its best. It puts us into the universe in ways we could not be otherwise. We will never visit Saturn. Almost certainly no living human ever will, not in any meaningful way, but we have visited, we have been there. A piece of our species, built by our hands, fell into the atmosphere of another planet and sent back its findings as it burned. Cassini is, in a literal sense, the only part of us that has ever been to Saturn. And what it learned, we learned. The data is ours now. The discoveries are ours. There is something else, too, that the final signal does to a person who thinks about it carefully. The 30 seconds of transmission that arrived after the spacecraft was supposed to have gone silent. Cassini was already dead, in the sense that the matter that made it up had already been torn into fragments and was diffusing into Saturn's atmosphere by the time the photons of the final signal arrived at the deep space network. Every word the spacecraft sent during those last 30 seconds was, by the time it reached Earth, an echo from something that no longer existed. The team in the control room was listening to a ghost. The ghost was telling them new things. The ghost was discovering things in its last moments and passing them along. That is not an abstract image. It is exactly what happened. The radio waves traveled for over an hour. By the time they arrived, Cassini was gone. The team heard the voice of a machine that, in real time, had ceased to be. The signal was, in a real way, the voice of something that had died still speaking. This is what makes the Cassini story haunting beyond all the science. It is not just about a planet far away. It is about a thing that humans made, that they sent into the dark, that did its job for 20 years, and that, in its final moments, told us something we did not know, and then was gone before its own words could reach our ears. It is a story about the durability of the things we make, even after the things themselves are destroyed. It is a story about how knowledge can outlive its source. And it is, in a way, a hopeful story. Because Cassini's final signal is also a reminder that what we build, what we send out, what we observe can survive us. The data is still being analyzed today. Discoveries are still being made from the readings. Almost a decade after the spacecraft burned up, scientists are still finding things in those numbers that they had not noticed before. Cassini is, in this sense, still working. The mission has not ended. It has only changed shape. The machine is gone, but the work it did continues, in laboratories on Earth, in papers being written, in young scientists who are dedicating their careers to the questions Cassini raised. That is the meaning of the final signal, not just for science, but for us. We made something. It saw the universe. It told us. It is gone. The telling remains. The questions Cassini left behind are larger than the questions it answered. This is what good missions do. They open more doors than they close. And the doors that Cassini opened are, in some cases, doors that no current spacecraft is on its way to walk through. The most pressing unanswered question is the one Cassini posed in its final 30 seconds. What was producing the heat and the unexpected chemistry in Saturn's upper atmosphere? The energy crisis of the giant planets has been a problem for over 3 decades, and the grand finale data narrowed the question without solving it. Whatever is heating Saturn's upper atmosphere is also driving a chemistry that the standard models cannot reproduce. Until another spacecraft flies into that region of the atmosphere, or until ground-based and space-based telescopes can study it with much higher resolution, the question stays open. And no mission to do this is currently approved. There are proposals, there are concepts, there is no funded project. The second open question is what created the rings. Cassini established that the rings are young and that they formed from the destruction of a body somewhere in the recent geological past. But the details of that event are completely unknown. Was it a moon that wandered too close and was torn apart by tidal forces? Was it a captured comet or icy body from the outer solar system? Was it an impact between 2 existing moons? Each of these possibilities predicts different details in the chemistry and structure of the rings. None of them have been definitively confirmed or ruled out. Studying the rings in finer detail, with instruments designed specifically to address the formation question, would require either a follow-up Saturn mission or extraordinarily detailed observations from Earth or Earth orbit. Both are currently off the table. The third open question concerns Saturn's magnetic field. The perfect alignment is real, but the mechanism producing it is not understood. Theorists have proposed the stable conducting layer idea. Others have proposed unusual coupling between the deep interior and the atmospheric winds. Others still have proposed that the field is in a slowly oscillating state, and Cassini caught it at a near-zero phase. Distinguishing between these possibilities would require either decades more of patient observation, watching to see if the field changes over time, or a mission that could measure the magnetic structure at multiple depths simultaneously. Neither approach is in development. The fourth open question is the chemistry of the rings themselves. Cassini detected complex organic molecules in the material falling from the rings into the atmosphere, but the instrument could not give a definitive identification. The mass spectrometer measured mass-to-charge ratios. To actually identify the molecules, you would need an instrument designed for that purpose, with the time and resolution to separate competing molecular candidates. A future mission could carry such an instrument. The Europa Clipper, currently on its way to Jupiter's moon Europa, carries a more advanced mass spectrometer than Cassini did. But Europa Clipper is not going to Saturn. It will study Europa for several years and then end its mission there. There are mission concepts that have been proposed but not funded. Enceladus Orbelander, a concept developed by NASA, would orbit Enceladus and then land on its surface, sampling the icy plumes directly and looking for biosignatures in the material. If approved, it would launch sometime in the late 2030s or 2040s. The Saturn probe mission, another concept, would send a small dedicated probe into Saturn's atmosphere to make the measurements Cassini could only hint at. It would gather chemistry data, temperature profiles, and wind measurements all the way down to depths where Cassini was destroyed within seconds. No version of this mission is currently funded. There have been white papers, proposals, and conference presentations, but no spacecraft is being built. The mission that is actually happening, and that owes its existence directly to Cassini, is Dragonfly. It is scheduled to launch in 2027 and arrive at Titan in 2034. Dragonfly is, in some ways, the most ambitious planetary mission NASA has ever attempted. It is a rotorcraft, a drone, a flying vehicle the size of a small car, powered by a radioisotope generator and carrying scientific instruments designed to study Titan's surface chemistry, atmosphere, and weather. It will not orbit, it will not roll, it will fly, hopping from location to location across Titan's surface, taking samples, measuring composition, photographing landscapes that no human has ever seen up close. Titan's atmosphere is dense enough, and its gravity low enough, that powered flight is actually easier there than on Mars. The decision to use a rotorcraft was, in some ways, a direct response to what Cassini's Huygens probe revealed when it landed on Titan in 2005. Huygens showed a world more complex, more varied, and more dynamic than anyone had expected. A static lander could not do justice to it, so Dragonfly will move. Dragonfly will not visit Saturn or its rings. It will not study the energy crisis or the magnetic field, but it will continue the Cassini story in another direction, on a moon that Cassini taught us was one of the most chemically interesting places in the solar system. It will look for prebiotic chemistry. It will study how complex organic molecules form and react in Titan's environment. It will be, in a sense, the next paragraph of the same long discovery. Beyond Dragonfly, the future of Saturn exploration is uncertain. There are pushes within the scientific community for a flagship-class mission to return, possibly an orbiter combined with atmospheric probes, possibly with a dedicated study of the rings and their evolution. NASA's most recent planetary decadal survey, the document that sets priorities for the field, identified a Uranus mission as the highest priority outer planet target for the next decade. Saturn missions are further down the list. The reasoning is straightforward. Cassini studied Saturn extensively. Uranus has been visited only once, briefly, by Voyager 2 in 1986. The community thinks Uranus deserves attention next. This is probably the right call scientifically, but it means that the questions Cassini raised in its final transmission may not get definitive answers for decades. The next dedicated Saturn mission, if it happens at all, will probably not launch until the 2040s or 2050s, and will not arrive until the 2050s or 2060s. The children alive today will be middle-aged by the time the next spacecraft from Earth visits Saturn. Some of the scientists who worked on Cassini will not live to see the follow-up. The data Cassini sent back in its final 30 seconds may have to carry the conversation alone for half a century. In the meantime, the existing data continues to be analyzed. New papers come out every year, finding details that had not been noticed in the earlier passes through the numbers. Machine learning techniques, which were less developed when the mission ended, are now being applied to the Cassini archive, revealing patterns that human analysts had missed. The Cassini data set is open. Researchers around the world can access it, study it, and publish their findings. In this way, the spacecraft is, in a sense, still working, not gathering new measurements, but having its old measurements reread again and again by new eyes. Telescopic observations from Earth and from space telescopes like Hubble and JWST also continue. They cannot replace a spacecraft at Saturn, but they can monitor the planet over time, watching for storms, tracking ring brightness, measuring the slow changes that take decades to detect. The James Webb Space Telescope has already made observations of Saturn that complement Cassini's measurements. Future telescopes will do more. The story is continuing slowly, through indirect means. But the deeper answers, the ones that Cassini hinted at in its last seconds and could not deliver, are waiting. They will need another machine, another long, expensive, audacious mission, another team of scientists willing to dedicate decades of their lives to a place they will never see in person. Whether that mission happens, and when, is a question for the next generation. Section 14:15. Step back from the science for a moment. Step back from the rings and the chemistry and the magnetic fields and the unanswered questions. Let yourself sit with what the Cassini story is at its heart in cosmic terms. A species evolved on a small rocky planet around an ordinary star. For most of its existence, that species was concerned with the things in front of it: food, shelter, other members of the species, survival from one day to the next. Almost none of its biology was designed to understand anything far away or anything long ago. Its eyes were tuned for the daylight on its own world. Its brain was tuned for the social arithmetic of small groups. There was nothing in its evolutionary history that prepared it to comprehend a gas giant 1 billion miles away. And yet, somehow, this species built a machine and sent it. The machine traveled for 7 years through cold and dark, alone, talking to its makers across delays of hours. It arrived. It stayed for 13 years. It looked at things that nobody on its home planet would ever see with their own eyes. It found that the world it was studying was both more beautiful and more strange than anyone had predicted. And then, when its fuel ran low, the species that built it made a decision. It would not let the machine drift, in case the machine, even by accident, contaminated a place where life might exist. So the species sent the machine to its death, deliberately, with ceremony. And the machine, in its final 30 seconds, kept doing what it had been built to do. It kept reading the atmosphere of the world it had spent its life studying. It kept sending the readings home. This is, when you look at it from far enough away, an astonishing thing for a species to do. There is no obvious evolutionary reason to send spacecraft to other planets. None of it provides food, mates, or shelter. None of it improves the immediate survival prospects of the people who pay for it. The motivation is something stranger, something that has to do with the fact that consciousness, once it arises, wants to look. It wants to see. It wants to know. It is not satisfied with the things in front of it. It pushes outward, asking what else is there, what is over the horizon, what is below the surface, what is above the clouds. The Cassini mission, and every mission like it, is an expression of that pushing. The universe, as far as we can tell, does not require us to look at it. We look anyway. We send our machines into the cold and the dark to look on our behalf, because we cannot all go ourselves, and we want, more than anything, to know. This is a strange kind of love. A species in love with a place it cannot visit. A team of scientists devoting their lives to a planet they will never touch. Engineers spending their careers building instruments that will be destroyed before they meet their builders again. Funding bodies committing billions of dollars for results that will not arrive for decades. None of this makes obvious sense by short-term reasoning. All of it makes sense if you understand that consciousness, having appeared, has a deep need to look outward. The need is not optional. It is what we are. Cassini sat in this need for 20 years. The machine, of course, did not love anything. The machine did not understand what it was doing. The machine was just doing its job, executing commands, taking measurements, sending the data. The love and the meaning were on this end. They were in the people. The people built the machine, and the machine carried their longing into a place they could not go. When it died in the service of that longing. There is something about this story that resembles older stories. Stories of people who built things knowing they would not live to see the finish. Cathedrals raised across centuries by stonecutters who knew the spires would be completed by their great-grandchildren. Books written for readers not yet born. Trees planted by gardeners who would never sit in their shade. Cassini fits in this tradition. The engineers who designed the spacecraft in the 1980s mostly retired before the grand finale. Some of them died during the mission. They knew, when they were designing it, that they were building something whose most important moments they would not be present to witness. They did it anyway. The mission belonged to a longer span of time than their individual lives. This is what makes the final signal so heavy when you sit with it. The 30 seconds of ghost transmission are not just data. They are the closing line of a multi-generational sentence. The sentence began in the early 1980s when scientists first started seriously planning a Saturn orbiter. It continued through the political fights, the engineering challenges, the launch in 1997, the 7-year transit, the 13 years at Saturn, and ended on September 15, 2017, with a machine being torn apart while still reading its instruments. The sentence is long. It involves thousands of people. It crosses lifetimes. The final signal is the period at the end of the sentence. And when you read the sentence as a whole, what it says is something like, "We tried to know, and we did for a while, and we sent what we learned home." There is a thought that comes to many people when they look at images from telescopes like Hubble, the deep field, the long exposures of galaxies stretching out in every direction. The thought is something like, we are very small. The universe is enormous. We do not matter. This is, in one sense, accurate. The universe is enormous. The Earth is small. The duration of our species is brief compared to the age of the cosmos. By any measure of scale, we are tiny. But there is another thought that I want to leave with you. The universe, as far as we can tell, is mostly empty space and unconscious matter. Most of it does not look at itself. Most of it does not know it exists. We do. We are one of the places, possibly the only place in our region of the galaxy, where the universe has assembled itself into a form that can think about its own existence. We are the universe trying to understand itself. And every spacecraft we send out, every telescope we point, every paper we publish, every video like this one that someone makes about a mission that ended years ago is part of that trying. The universe is using our brains to look at itself. And when we send out a Cassini, we are the universe sending out a probe to study its own gas giant. We are the cosmos reaching, with its small conscious tendrils, into the rest of itself. This does not have to mean anything supernatural. You can hold this thought as a metaphor or as a literal description, depending on what you believe. But the underlying fact is the same. Wherever consciousness exists, the universe is no longer purely unwitnessed. It has witnesses. And the witnesses, in their brief lives, do incredible things. They build cathedrals. They write books. They send machines to other planets and listen to the machines die, sending back readings until the last instant. They take what their machines learn and they share it with each other, in classrooms, in journals, in videos late at night, so that the knowing belongs to the species and not just to the individuals. Cassini was part of this. The final signal was part of this. And you, sitting here listening, are part of this. Section 1515 tonight, we have traveled with a machine that no longer exists. We have followed Cassini from the rooms where it was first imagined in the early 1980s, through the political fights and the engineering trials, the launch in 1997, and the 7-year journey through the inner solar system, the arrival at Saturn in 2004, and the 13 long years of patient watching. We have walked beside it through the close passes of the grand finale, through the gap between the planet and its rings, into the upper atmosphere itself, and we have listened, alongside the team at the Jet Propulsion Laboratory, to the final 30 seconds of transmission that arrived an hour and a half after the spacecraft had already been destroyed. We have looked at what those final seconds contained. The ring rain pouring complex chemistry into the planet, faster and richer than any model had predicted. The fuzzy core, the smeared-out interior where rock and gas blend together in a way that overturns the textbook picture of how gas giants are built. The perfectly aligned magnetic field, an arrangement that classical physics says should not be possible, sustained by some hidden mechanism we still cannot fully describe. The unexplained heating in the upper atmosphere, paired with molecular signatures that the standard chemistry does not produce. The two anomalies linked in ways that suggest some unknown process is at work. And threading through all of these discoveries, the realization that Saturn's rings are young, that they appeared in geologically recent time, that they are dying in geologically recent time, and that we are alive during the brief, glittering middle of an event whose beginning and end are both invisible to us. This is a great deal of information to carry. But what I hope stays with you after the specific facts fade is something simpler, a feeling, a sense. The sense is something like this. The universe is older and stranger than the textbooks have time to tell you. The planets you grew up looking at in posters and picture books are not as fixed as they seem. The most iconic features of the solar system are passing through. The Saturn that Galileo saw in 1610 is the Saturn that you can see tonight if you have a telescope. But it is not the Saturn that existed 1 billion years ago, and it is not the Saturn that will exist 1 billion years from now. We are looking at a slice of a much longer story. We are inside the slice. The slice is what we see, and what we will ever see in our short lives. But the slice is only a slice. The story is much bigger. And we, this species, on this one small planet, built a machine to look. We built it knowing it would die. We sent it across distances that our biology cannot really comprehend. We listened to it for 20 years. We sent it to its grave with deliberate care. We received its final words from a place that, by the time the words arrived, no longer held anything of the machine but the diffusing fragments of its body. And from those final words, we learned things that none of our ancestors ever knew, things that our descendants will be analyzing for decades to come. I find this beautiful. I hope you find this beautiful too. Not in a sentimental way, but in the way that great events are beautiful, the way that long stories told well are beautiful, the way that small acts of devotion to large ideas are beautiful. Cassini was a small act of devotion to a very large idea. The idea is that consciousness, having appeared in the universe, should not be content to remain ignorant. The idea is that we should look. The idea is that we should send out our instruments and our questions and our patient listeners, and we should keep doing this even when the answers will not come back in our lifetimes, even when the spacecraft will die before its job is finished, even when the data will outlive us all. The next time you see Saturn in the sky, do me a favor. If you happen to be somewhere dark enough, on a clear night, look up and find it. It will be a yellowish point of light, not blinking, steady, somewhere along the path the planets take across the sky. It will look unremarkable, just another light. But you will know, in a way that almost no one in human history before our generation has known, that what you are looking at is a temporary spectacle. The rings you cannot see with your naked eye are bleeding into the planet at thousands of kilograms per second. The atmosphere is being chemically transformed by their fall. The interior is a fuzzy blend rather than a clean core. The magnetic field is perfectly aligned in a way that physics still cannot fully explain. And in the upper atmosphere of that distant world, something we still do not understand is producing heat and complex molecules in linked patterns in a region of the planet that a machine we built passed through briefly before it died, sending its readings home in the last 30 seconds of its life. That is a lot to think about, looking at one yellowish point of light. But all of it is true. All of it is yours to know. Thank you for spending this time with me tonight, walking through the story of Cassini's final signal and what it gave us. If this journey moved you, if it made you look at the night sky a little differently, if it made you think about what we build and what we send and what we leave behind, please take a moment to like this video and subscribe to the channel. Stories like this one take a long time to put together, and your support, however small it may feel, is the thing that allows me to keep telling them. Every like, every subscription, every comment helps these explorations reach more people who, like you, are willing to sit through the long version of a story instead of the short one. If there is a planet you would like me to explore in a future video, or a mission whose ending you would like to revisit, leave it in the comments. I read them, and I take requests seriously. There are many stories out there. Voyager is still flying. Juno is still circling Jupiter. New Horizons is still receding into the dark beyond Pluto. Each of them has its own tale, its own final chapter waiting to be written. We can walk through any of them together. Sleep well tonight. Remember that 4 billion years ago, the solar system formed in a chaos that nobody witnessed. Remember that 150 million years ago, something happened at Saturn that gave it the rings we see today. Remember that in 1997, a machine left Earth, and that in 2017, that machine died in the atmosphere of another world, still talking, still listening, until the very last second. Remember that the universe is full of brief, gorgeous events, and that you are alive during one of them, watching another one happen far away. Remember that the rings of Saturn are temporary, so is everything else. So are you, and so am I, and so are all the things we love. But for a little while, all of it is here, all of it is real, and all of it can be seen if you take the time to look. Good night, and may you keep looking up.